All right, so yeah, the blue box around the drop-down menu, yeah, that's kind of weird. So I'll try to, work on it more. It's something I wanted to do once we started this semester, but I never had time until this past weekend. Yeah, it looks a little weird. I know there is a better way to kind of solve it, but I don't know too much about HTML. Well, pretty much know nothing. Okay, so we got 30 people in here right now. Should have a few more. So today we're just gonna go over, like we always do, we're gonna start out with a review, and then I'm gonna also have a poll for the quiz time that we had last time. Whether it's too short, which I doubt anyone's gonna say that, or sorry, too long. I doubt anyone's gonna say it's too long, but I want to see if you thought it was too short. And then we're gonna keep going over arrays, and we're gonna finish arrays this week. At least that's the plan. All right, so I'm actually gonna put the poll up right now. So again, I want to see your opinion on the time duration for last week's quiz. Was that last week or the week before? I already forget. I think the week before. So I can see how long everyone took on the quiz, but that's kind of different than actually hearing your feedback too. Okay, so we got most people say just right. And we got a fair amount of people saying too short. So I might make this week's quiz, if I have the same amount of questions basically, or the same amount of work involved, I'll make it 20 minutes, or I'll just have a few less questions. Okay, I'm gonna end it. Okay, so let's get started for today. Share my screen. All right. Okay, so I updated the slides again late last night. When I update them, it's usually pretty late. Okay, so we're gonna, let's first go back here. So the plan, just a few reminders first. Homework 2, that's due today by 11:59 p.m. I asked you guys in the Discord if you thought it was okay, and it seems like most of you think the homework is pretty good so far. Quiz 2, that's this Wednesday, so be prepared for that. And that's going to cover basically everything on the homework and everything that we covered in class up to the basically up to the end of last time. I'll do that. So anything that we covered today won't be on the quiz. And then, yeah, so this week we're going to finish chapter 2. That's for arrays. At least that's the plan. It might take a little longer, but we don't have too much left. Okay, so I had a question on the homepage for our class here, because I kind of changed it a bit. So I only changed 2 things right now, but class links and homework solutions, you'll see that they're actually clickable links here. So they're basically a drop-down menu. So if you click on class links, it's going to have a drop-down menu. Well, right now it has a drop-down menu for both of these right away, which isn't what I want. But either way, it's a drop-down menu right now. So just so it kind of declutters the homepage here. I'm going to try to fix this so it looks a bit better and doesn't have this blue box around it. And basically, if we just click on, homework solutions, only that drop-down menu shows up. But if you were a little confused today why you couldn't see the class meeting here for Zoom, that's why. Okay, so let's get started. Okay, so we're going to start out with this review exercise. So I want you to make these two arrays and then at least attempt to do all 4 of these exercises. You may or may not be able to do some of these. You might get an error. So I want you to think of why you have an error if you do. All right, I'll give you like 3 to 5 minutes. Okay, we have question. When is our first project? So I'll probably start talking about the first project sometime, I don't know, next week. We're going to have the first project after we finish chapter 5, which is plotting. So we're going to finish chapter 2, which is arrays, and then we're going to go over chapter 5, that's plotting. Once we're done with that, then we're going to have the first project. So it's probably like 2 or 3 weeks out from now. But I'll talk about it probably next week. Okay, so I'm going to assume that all of you are done, because it's not too much here. But let's go over it. Does anyone have any other questions before I guess we get started, either on the homework, the quiz this Wednesday, or the class in general? Okay. So we have A equals 4, 2, 8, and B equals 2, 6, 1. All right, so we have these two vectors. Okay, and then we want to see if we can do matrix multiplication. So if we look at this right now, we have a 1 by 3 and a 1 by 3. So if we try to do A times B, then that's not going to work because our dimensions aren't the same. So instead, if I do A times B transpose, that will work because our dimensions are the same then. So let me actually advance the slide. So matrix multiplication of A times B transpose, that's going to work because our dimensions are maybe I shouldn't say they aren't the same, but they're compatible. So we have a 1 by 3 row vector multiplied by a 3 by 1 column vector if we do A times B transpose. So remember, so I kind of show it right here. If we do that, our inner numbers, they match. So that means we can do that matrix multiplication. And then our outer numbers, they are 1 by 1. So that means our output is going to be 1 by 1 or a scalar. And so up here, when we tried doing A times B, that was a 1 by 3 times a 1 by 3. So those inner numbers, they didn't match. So we couldn't do it. Get these back. Okay, so if we do array multiplication of A times B, that's going to be A dot star B. So remember this dot star, that's our array multiplication. So if we're doing an array option, we have this little period right there. Okay, so if we do that, that's going to work. So remember for an array operation, or specifically array multiplication, that multiplies each element for the array. So it goes index by index. So we have 4 times 2 is 8. Then it goes to the next index. So 2 times 6 is 12. Then we go to the next index. So 8 times 1 is 8. All right, then we get that. So we have another one. We have array multiplication of A times B transpose. So if we do that, oops, didn't put transpose. So if we do that, then that also works. Now we get a 3 by 3 matrix. So this is going to basically show up like that. So for this, remember it's going element by element. So, here, if you look at what we're doing, we have a 1 by 3, and then we have a 3 by 1. And our output is a matrix. So remember here we're doing element by element multiplication. So that's why our size isn't what we had up here for A times B. So let me actually do that. Okay, so A times B transpose, remember that was just an array, or sorry, not an array, but that was a scalar output. And here, A times B transpose, doing element by element, that's a 3 by 3 matrix. Remember that we're doing each index. So this multiplication works, a bit different. We're doing 4 times 2, that's 8. And then we're doing 6 times 4, and then 1 times 4. And that's our first column. Then we go column by column. So for this, I think it would make more sense if you kind of write it out and you go through it like that. Okay, so yeah, someone couldn't find the Zoom link. I probably should have sent in an announcement to tell you guys. But yeah, it's a drop down now on Canvas. So if you click on class links on Canvas, that's a drop down menu. Okay. Okay, we have another slide here. So go through this and then we'll go over this as well. So I'll give you, again, like 3 to 5 minutes to work on this one. Okay, so I'm gonna go over it now. So hopefully all of you finished it and also thought about whether these operations did or didn't work. So let's go over it. So the first one we have is matrix multiplication of A times B. So this one is going to work. So if we look at let's look at the slide here. So our dimensions for A are 3 by 2. We have 3 rows and 2 columns. And the dimensions for B, they are 2 by 2. So we have 2 rows and 2 columns. So if we do this matrix multiplication, our inner numbers here, that's 2 and 2. So that's going to work. And then our outer numbers are 3 by 2. So the output should be a 3 by 2. So let's do that. So we'll do A times B, and that's what we get. We have 3 rows and then 2 columns, so that works for us. Okay, if we try matrix multiplication of B times A, that's not going to work now. So the error that we get says incorrect dimensions. So here, if we look at what we had a 2 by 2, that was matrix B, multiplied by a 3 by 2, which is matrix A. So those inner numbers right there, we have 2 and 3, they don't match up, so that's not going to work for us. So we can't do that. And then we're going to try array multiplication. So remember, array multiplication, that's the same as saying element by element multiplication. So if I use either word, I mean the same thing. So we'll do A dot star B. And that's not going to work. It says matrix dimensions must agree. Let's try B dot star A. That's also not going to work because our matrix dimensions must agree. So if I go back in the slides here, it's somewhere here. Let's see here. Okay, yeah, so we said 4 from last class. For element by element multiplication, it's only defined in MATLAB for arrays that are the same size. So if you want to do an array operation, they have to be the same size. In this case, they weren't. We had a 3 by 2 and a 2 by 2, so they are different sizes, so that's not going to work. Okay, any questions on these 2 exercises? Okay. All right, so now we're going to talk about vectorized functions. So far in MATLAB, we've been using functions like the square root or the exponential or trigonometric functions. And behind the scenes, they've been doing element by element operations. So let's define an array here. So we'll do x equals 0. We're going to use a step size of 1, and then we're going to go to 5. So just to review, this is going to make a row vector from 0 to 5 with a step size of 1. And then I'm going to show you that the length of this is 6. So we'll do length of x, that's 6. Now if I type in sine of x, that's doing an element by element operation. So it's taking our row vector x, and then since we just did sine of x, it's going to compute the sine of each element that we have. So it's going to go sine of 0, that's 0, and then sine of 1, and it's going to go through to sine of 5. So yeah, it's doing that element by element. So even though we didn't specify to do an element by element operation, it's doing that by default. Okay. And then if we did something to like the square root of x, that'll do the same thing. It's going to go element by element. Now if we are going to do an operation between functions like this, then we have to specify an element by element operation. So let's do, if I do a sine of x times exponent of x, then it says that we have an error. It says incorrect dimensions for matrix multiplication. In this case, we want to do an element by element multiplication. So we would have to do sine of x dot star exponent of x. And now if we do that, then that's going to work for us. So we have to do this because sine of x and exponent of x, behind the scenes, they are doing an element by element operation. So if we are multiplying those 2 functions, then we have to use array multiplication. So we have to include that dot right there. Okay, so any questions on that? I think, you know, at least for me, when I first went over this, when I took this class, I thought it was a little kind of weird at first, but it makes more sense if you think about sine of x and exponent of x. They're carrying out an array operation of their own. So if we want to do an operation between the two, then we have to specify an array operation. So that's why we're putting that dot. So we'll do one more exercise right now just so we can kind of understand this a bit more. So I'm going to do a equals, we'll do 0 to 10. And then remember, by default, doing this operation here for using a colon operator, if I do a equals 0 to 10, that's going to give us a step size of 1. And that's going to go from 0 to 10. So our length here is 11. Okay, and then I'll do another here. B equals pi, I don't know, 2 times pi. Okay, so here we have b equals pi to 2 times pi. Well, I want to make this the same length, so let's rewrite this. So I'm going to clear everything, so a equals 0 to 10, and I can do b equals pi, and I can do the length of a 2 times pi. That didn't work. Okay, let's scratch that, sorry. Let's do a equals 0 to 10, and then b equals, we'll do 2 to 20. Okay, so let's do an operation here. So we'll do cosine of a, and now if I did divided by b, or sine of b, that's going to say our matrix dimensions must agree. So instead we'll do cosine of a divided by sine of b, and this also shouldn't work right now because our length there is different. So I do b equals we'll do one space 2 to 20, and then we're going to do length of a. Okay, so now we have a row vector a, that's from 0 to 10, and we have a row vector b, and I wanted to make that the same length as the length that we had for a. So because of that, I used the linspace command. So I have a row vector starting from 2 and it's going to 20, and the length of this is going to be the length of a, so I can match them up. So if I look in the workspace, we have a 1 by 11 double for a, and we have a 1 by 11 double for b. Okay, so now if I do cosine of a divided by sine of b, and I do array division, now that's going to work for us. Okay, so it's carrying out this division for these trig functions, element by element. So if I did the length of our answer here, that's going to give us a length of 11. So the length stayed the same. Okay, I think I have an exercise, yeah. Okay, so I was going to have you do this on your own, but I already have this whole slide that's showing up here. So we'll just go through it as a class. So if we define a vector here from 0 to 5, so we're doing that again. So we have our vector here, and the length of this is 6. If I do sine of x times cosine of x, that's not going to work right now because we have these vectorized functions. So remember, sine of x and cosine of x, they're already doing an element by element operation by themselves, kind of behind the scenes. So if we want this multiplication to work, we're going to do sine of x dot star cosine of x, and now that's going to work. Okay, so now I have this exercise for you guys to work on. So I'll give you a few minutes to work on this and then we'll talk about it. All right, I'm going to give you about 30 more seconds. Okay, so let's go over this right now. Okay, I'm going to clear everything. Okay, so what we have to do is first to define an array of x from 0 to 20 with the step size of pi. So we'll do x equals 0. Our step size is pi, and then we want to go to 20. Okay, so there's our vector. That's going to be a row vector. Then I'll define y. So now I want to do an operation with this row vector that we just made. So I can do just y equals sine of x. That's fine. But now I want to do sine of x times e to the x. So both of these sine of x and e to the x, they're vectorized functions. So if I want to multiply these vectorized functions, then I need to do array multiplication. So I'm going to do dot star exponent of x, or that's, e to the x. Then I can do plus exponent, or e, to 2 times x. So you'll see right here, in this case, I just put a plus on it. I didn't put a dot plus. So in one of our slides before, and either last class or the class before that, I forget, addition and subtraction, that's the same for, regular addition and subtraction, or element by element addition and subtraction. So because of that, I'm just putting a plus sign right there. And then we're going to do dot star times cosine of x. So again, right here, I'm doing multiplication. So because of that, I need to do dot star. And then we're raising this to a power of 2. In this case, I also need to do an array operation. So I'll do dot and then squared. And then if we press enter and we run that, then that works. So now the length of these should be the same. So I'll do length of x and length of y. And both of those are the same. Or I could have done size of x and size of y like I show on the slide. So size of x and size of y, they're both 1 by 7. So we have one row with 7 columns. Okay, so hopefully that exercise here kind of helped you understand this a bit more.
Sorry, Professor, I just don't really understand. Like, I sort of understand why we use the dot star, but I want to know why would we use the dot to the power of 2 and things like that, at least in this situation.
Mm-hmm. So in this case, we, right here for cosine of x squared, that's really cosine squared of x, as we see up here. So if we go back in the slides here, MATLAB, they require us, if we want to use these element by element operations, that if we divide, multiply, or raise these functions to a power, then we have to use the element by element operator. So you just need to remember that if we're multiplying some of these functions, these vectorized functions, so that's stuff like square root of x, exponent of x, or any trig functions, then we have to use that dot. So if we have sine of x, if we wanted to use sine square of x, so if I try that, that's not going to work because just like in the slide here, MATLAB is saying that we have to do an array operation here. So we have to use that dot. So we're doing instead sine of x dot squared, and then that's going to work. So we have to do that because this operation is going element by element in the background. So that's how we have to specify that dot. It might be a little confusing at first, but just at least for now, you just should remember that because this is a vectorized function, we have to do that dot.
Okay,
Does it
thank
make
you,
a little more
Professor.
sense?
Yeah.
Okay.
So if we see there's an array, we have to put the dot. But if it says multiplication one, we just use the star only, not the dot.
Yeah, so we have matrix multiplication or some matrix operation. And so yeah, let's clear this. So if I said do matrix multiplication of some arrays like x times y, then that would be x star y. If I tell you to do array multiplication or element by element multiplication, then you have to do dot star y. That makes sense?
Yeah.
Okay. So yeah, we have matrix multiplication, and then so that's 1. And then we have array multiplication or element by element multiplication. So that's the same thing. So I might use either term, but that's the same.
I wrote the same thing you did, and I don't know why it says dot index is not supported for variables of this type.
Okay, so you're talking about for this exercise here, right?
Yeah,
It says it's not supported for that type.
yeah, with the dot.
Are you using MATLAB 2020A too?
2019?
Okay, that should be supported. So stick around after class and then I'll try to figure that out with you because that should work.
Okay, thank you.
All right, so now we're going to talk about element by element division. So this is going to be similar to multiplication. So if we're doing, again, element by element division, that's going to go element by element like the name implies. So if we have two arrays here, so we'll do A and B, A equals 8, 4, 2, 10. B equals 8, 2, 1, negative 5. So here we have two row vectors that are 1 by 5. So if I want to do array division between the two, then we just do A dot / B. And then that's going to do division for each index for these arrays. So it's going to start in this first index, do 8 divided by 8 is 1. Then it'll go to the second index, do 4 divided by 2 is 2. Go to the third index, 2 divided by 1 is 2. And then the last index, 10 divided by -5 is -2. So it's similar to what we just did for matrix multiplication, but of course this time we're just doing it for division. Okay, so we have another exercise, so I'll give you about a minute to work on this one. Okay, so that should have been pretty quick, so I'll just go over it now. So we have a column vector x, so we have 2, 4, 5. And then we have a row vector y, so y equals -2, 1, 5. Okay, so we're doing array division between the two, so we have x divided by y. So I need to do x / y, x dot / y. That's going to give us a 3 by 3 matrix. So remember that array division is similar to array multiplication. We're just doing division. So here we have a 3 by 1 column vector x, and then we have a 1 by 3 row vector y. So our outside numbers are 3, so that's going to give us a 3 by 3 output. So we're just to kind of go over this and see what the math is doing. We have x divided by y, so we're doing 2 divided by -2 as -1, and then we're going 2 divided by 1 is 2, and 2 divided by 5 is 0.4, and we're going to go to the next index in x, and we're going to go 4 divided by -2 is -2, 4 divided by 1 is 4 divided by 5, and we're just going to keep going like that. Okay, so it looks like we got another exercise here. I guess we got a lot, so I think that'll be good though. Kind of reinforce this stuff in your head. Okay, so work on this one. Even though I already showed you the answer. Okay, so I'm just going to go over this now since I already spoiled the answer anyways on the slide. Okay, so we have two vectors here. We have x and y. So we're going to define these vectors, and then we're going to have this operation here. So we're going to do sine of x plus e to the x squared divided by cosine of x. Or sorry, cosine of y. So we're going to first define our vector x. So we have x from 3 to 59 with a step size of 0.5. So we can just use our colon operator that we've been using for a while. So 3, our step size is 0.5, and then we're going to go to 59. So if I click on x, we're starting at 3, and then we see our step size is 0.5, and we're going to 59. So for this line, you already saw me do something like this earlier on, but I want to have a vector y from 4 to 20, and I want it to have the same length of x. So, just off the cuff, I wouldn't know what that step size is, but I know I want to have this vector y to be the same length as x. So I might want that just so I can do, operations between the two, like multiplication and division, or if I'm just making some arrays and I want to plot them, they have to be the same length. So using linspace here and doing 420, and then for our length argument, I can just type in length of x, and then that's going to ensure that our length here for y is going to be the same length as x. And if we look at the workspace, we have x is 1 by 113 and y is 1 by 113. Okay, so then we have our math operation here. So we have sine of x, so we can just do it like that, and that's going to work for us. So let's just show you this. So sine of x, that's going to be a 1 by 113 double. But let's do our operation now. So we have sine of x, and we have plus. Remember, for addition and subtraction, array addition and subtraction is the same as regular addition and subtraction. So I just need to put a plus sign right there. Then we have plus e to the x squared. So I have e to the e to the x, so that's what we have right now, e to the x, and now I need to square that. So because of that, I'm raising it to a power, just like we talked about before for a vectorized function. If we're raising that to a power, we need to use an array operation. So we're going to put x dot squared. And then we want to divide that by cosine of y. So again, we are using vectorized functions here. So I'm going to put dot and then a forward slash and then cosine of y. If we run that, then that works. Let's assign this a variable. And then our answer z is also a 1 by 113 double. Okay, any questions? Hopefully, we've had a few exercises now, so hopefully that kind of cemented this in your mind. All right. All right, so I guess I have a note here. If you did this operation, then all of our outputs would be NaN. NaN just means not a number. So that would kind of tip you off that we need to do an element by element operation. So you see the difference here is I just did divided by cosine of y and not a dot and then a slash. Okay, so we have a question. Why don't we do e to the dot x, so like this. So you'll see there it says invalid use of operator. So functions like this are vectorized functions. By default, if we're just typing out that function, it's going to work on an element by element basis. So if I do just exponent of x, then I should have suppressed that. That's just gonna work element by default. So let's go back here. So we need to use the dot if we're doing an operation between two functions. So e to the x right here, that works by itself. But if I want to do e to the x multiplied by another vectorized function, then I have to put that dot. So dot sine of x. Okay, so that's when I have to put that dot before the multiplication sign. If I do exponent of x times sine of x, then that's not going to work now. Does that answer your question? Okay. All right, so we already talked about this first part here. So if we're raising some array to a power, then we have to use our element by element operation. So here we have x equals 2, 3, 4. If I want to raise that to the third power, then I do x dot 3. And that gives us 8, 27, 64. So that's doing 2 to the third is 8, 3 to the third is 27, 4 to the third is 64. And this is also going to work for a matrix. So if we have a matrix A, which is 3, 4, 5, 2, negative 9, 10. If I want to square each element in this matrix, I just do A dot squared, and that'll square each element in the matrix. All right, so I think that kind of carries over, pretty intuitively from a vector to a matrix. All right, so if we just tried x to the third, then we're going to get this error. And again, that's just because we know from our first slide here, if we go back to this slide, it says if we want to multiply, divide, or raise a vectorized function to a power, then we need to use the element by element operator. Okay. And then if I did a squared, that's not going to work. Again, I need to use that period. Okay, so I also say if we have a square matrix, then we could raise that matrix to a scalar power without specifying that element by element operation. So let's clear this. I'll type in A. Or I need to modify that to be square. So something I can do here, if I want to just have this matrix be these first two rows and first two columns, I can modify this by doing A, we'll do all of the rows in the third column equals these empty brackets. So now our matrix A is updated to just have the first two rows in the first two columns. I'm not going to test you on this. This is just something that's useful to know. Okay, so I can now do, again, our matrix A is 2 by 2 now. So I can do A squared, and now that's going to work for us. And really what this is it's just multiplying A by A. So A squared is the same as A times A. And so A squared is working for us because our inner numbers, they're the same. We have a 2 by 2 times a 2 by 2. So those inner numbers, they're 2 by 2. So we know that multiplication is going to work. And our outer numbers are 2 and 2. So the output is a 2 by 2 matrix. So to recap, if I have some array here, let's do a 2 by 3. So 2, 2, 2, sure. And then 3, 9, 8. So if I have this matrix here, that's 2 by 3. And then if I have another matrix, B equals 9, 0, 8, 9. So if I try A squared, that's not going to work. But if I try B squared, that will work because it's a square matrix. All right. Also, maybe some of you saw I was starting to type out the word magic. This is just another side note here. So I can do A equals magic of 5. And what this is doing is creating a 5 by 5 matrix. And I think the maximum value we can have here is whatever number that you put in for the argument squared. So in this case, it's 25. So again, just another side note, I've never used this until yesterday, but it's kind of convenient if you just want to make some square matrix without typing everything in. All right, so we can also do, we can have a scalar and we can raise that to an array power. All right, so if we have some matrix or some vector R of 2, 4, 10. So here we have a row vector R. So let's say I'm going to have a scalar such as 2, and I want to raise that to an array power. So if I do 2 raised to the R, so raised to that array R, that's going to go element by element. So it's going to create a vector now, where we have 2 squared, and then we have 2 to the 4th, and then 2 to the 10th. All right, so we can do that as well. And we can do the same for a matrix. Also, if I just tried 2 raised to the R, again, that's not going to work because we have to go element by element. So let's do it for a matrix now. So let's define this matrix W. We have 2, 0, 8, 3, 4, 10. I put 2, 4, 10, whatever. And then I can raise a scalar to that matrix power by doing 3 raised to that matrix. That's going to work as well. So we have 3 squared is 9. 3 to the 0, that's just going to be 1. 3 to the 8th, 6,561. You get the picture. We're going element by element now. Okay, so I already showed you this. If we did 2 to the R or 3 to the W, we're going to get errors because we have to go element by element. But again, if we have a square matrix, then we can do that without specifying that dot, because we're essentially raising it to, and you can kind of think of it like a matrix power, I guess. So if we have A equals 2, 4, 8, or 9, 10, whatever, it doesn't matter. So if we have that square matrix, then I can have a scalar and I can raise that to this matrix A. And because it's a square matrix, that's going to work for us. Okay, I feel like this is a bit tedious, but I guess we got another one. So we got a lot of stuff doing these element by element operations between between each other. So we only have 2 more slides though for this element by element stuff. So you're almost done. All right, so we can do element by element exponentiation between 2 arrays, only if the dimensions are the same. So if we have A equals 2, 4, 6, and we have B equals 1, 2, 3. So we have 2 row vectors here. They're both 1 by 3. So I can do A raised to the power of B. And then we have 2 to the first is 2. And then we have 4 squared is 16. And then 6 to the third is 216. Okay, so you can kind of see how that's going. We're going element by element, but we're raising it to some power. I could do B to the A. And then we have 1 squared is just 1, 2 to the 4th is 16, and 3 to the 6th is 729. And okay, to reiterate, the sizes, they have to be the same. Why? Because we're going element by element. If one matrix is some length and the other is 1 less, then I can't go element by element because I'm missing some index in one of those arrays. So in this slide here, if I try doing this, it's not going to work because I have no fourth element in array A. So MATLAB doesn't know what to do. Okay, so now we're done with that part. I think it was kind of a lot. So yeah. All right, so now we have the identity matrix. So we have we're gonna go over some special matrices that we have inside of MATLAB, or really, in math in general. So right here, I put also look up symmetric matrix. That was really a note to myself that I forgot to take out. I'll show you how we can kind of make a symmetric matrix inside of MATLAB. I wanted to see if there is a more convenient way to do it. And from what I've seen, there's not really, but I'll show you how to make that as well. Okay, so first off, let's talk about the identity matrix. So if you haven't taken 250B yet, then maybe you haven't seen this yet, but it's essentially if we have some matrix and we want to multiply that matrix by, in quotes, 1, then that's going to be this identity matrix here. All right, so that's just a matrix where we have ones along the diagonal. And to create this, all we have to do is use the command I. So if I do I of 3, then that'll make a 3 by 3 matrix where we have 1 along the diagonal. If I do I of 5, then we have a 5 by 5 matrix here. Okay, so that's going to work. If I have some row vector from 0 to 10, okay, we have that. I could also do I of size of x, and then that's going to make our identity matrix here the same size as x. Yeah, so what I should have actually done is the length of x, because right now size of x is, it's going to be 1 and 11. So really what I should do is I length of x, and then that's going to give us an 11 by 11 identity matrix right here. So I'm going to go back and I'll update this slide. This should really say length of A, not size of A. Okay, so the symmetric matrix. So this is actually relevant because right now in one of my classes, I have to make symmetric matrices. It's for a finite element class. So, it was relevant to me, so I looked this up. And I guess this just goes to show you too, from what I've been saying so far this semester, that, learning MATLAB is going to be very useful for some of your other classes that you take. Okay, so to make a symmetric matrix, like I said, I couldn't find a really convenient way to make it, just because you have to specify some of the elements that you want to have in your matrix. So let's make a matrix here. I'll do A equals 3, 0, 3, 2, 3, 2, 9, 0, 9. All right, so there's our matrix. So what I can do is we'll do B equals zeros of 3, 3. That's going to give us a matrix of zeros here, which is 3 by 3. That's actually the next slide here. And then if I want to make this symmetric matrix, so basically I want to make this matrix A here. Really I shouldn't have defined it like this, because this obviously isn't symmetric. You know what, instead I'll make another video at a different time to show you this, because really this isn't, anything you're going to be tested on. But basically what I would do is I would first make this matrix B, which is full of zeros. Then I would define elements in this first index, the second index, the third index, and then this index right here, this index here, and this index here. And then I would update my matrix B to have all of those elements, and then add in all of those elements, but then transposed. And then that would make my symmetric matrix. But again, and that's another thing, just kind of as an aside. Okay, so we'll talk about making this zeros matrix here. So you see I already made it, but if we want to make a matrix full of zeros, then all we have to do is use that command 0. So I can do A equals zeros of 3, and that'll just make a 3 by 3 matrix. Or I can actually specify the amount of rows and the amount of columns like I did, just a few minutes ago. So I can do B equals zeros 5, 7. That'll have 5 rows and 7 columns. Or I can do zeros for the size of something else. So at this time we are going to use the command size. So I can do z equals zeros size of x. If you see in our workspace, that's a 1 by 11 double. I should change this. So we'll do c equals zeros because we want a matrix. Size of A. And then that'll give us a 3 by 3 matrix because the size of this matrix A is 3 by 3. Okay, so when is this useful to do? It is very useful in MATLAB. So we're going to do this often when we want to initialize a matrix to have all zeros. So you're going to do that when you want to use a for loop, and that'll be chapter 4, I think, and we're going to go over that later on in the semester. So you're going to use that when you want to initialize this for loop. It's basically going to save on computation time. Or it's useful if you don't know the dimensions ahead of time. So let's clear everything. I can have A equals zeros of 4, and that'll make a matrix of that's 4 by 4 that's filled with zeros. All right, that was in the way, but I kind of clear it. Okay, let's do that again. So we have A equals zeros of 4. Okay, so we have a 4 by 4 matrix of zeros. So I could just put in that arbitrary amount, but later on, if I then know the dimensions in that array, so let's just add some stuff now. I can just do A equals 3, 4, 5, 2, 0, 2. And then we have this matrix here. So you can kind of think of this like a just a placeholder if we don't know the dimensions ahead of time. All right, so we have the identity and the null matrix. So our matrix of zeros, that was the null matrix. That's what it's called. So these are the properties of those matrices. So if I do 0 times A, so 0 being just 0 multiplied by A, whether it's the identity matrix or the null matrix, that's going to equal 0. And then I can do the identity matrix times some matrix that's going to be equal to A times I or equal to A. So let's, I have this matrix A here. So if I multiply that by some identity matrix, we'll do B equals, no, let's change this. So let's make a 3 by 3 matrix A. Okay, so we have a 3 by 3 matrix A here. And we'll do B, that's a 3 by 3 matrix, but it's the identity matrix. If I do A times B, then that's just our matrix up here, our matrix A. So that's, why I said it's kind of like multiplying some matrix by 1 in quotes. And then back here, I also showed that the zeros matrix, that's different than the empty matrix, which has no elements. So these brackets with nothing inside, that's just to signify that there's nothing in there. Okay, so we had the identity matrix, and then we had the zeros matrix. We can also have a matrix filled with ones. So I haven't used this very often, to be honest, but there might be some cases where you do want to use it a lot. All right, so I can do 1s of 10, and that'll give us a 10 by 10 matrix filled with 1s. Or I can specify the amount of rows and the amount of columns, so 1s of 2, 3, and we have a 2 by 3 matrix of 1s. Or again, I can specify the size by using the size of some other matrix. Okay, before we do this exercise, are there any questions on these matrices? Okay, if not, then I just want you to work through this exercise. I forgot to break up the slide again. So I already showed the answers. So let's go over it now. All right, so I want you to make a matrix that's 5 by 5 filled with zeros. That's just going to be A equals zeros of 5. Or we could just do zeros of 5 comma 5. Same thing. If we want to make the identity matrix B, that's the same size as A. B equals I, size of A. So we want to use the I, that means identity matrix, and then the size is going to be the same size as matrix A right here. So that'll be a 5 by 5. And then we can do a 10 by 5 matrix C of 1. So C equals 1's 10 comma 5. We're going to have 10 rows, 5 columns. All right, so now we are on linear algebraic equations. So this is also something that's going to be useful in your classes. Again, this is something that I'm doing right now for the class I'm taking for finite elements. So that's EGME 541, by the way. There's also a 400 level class for finite element, but I think that's more like based on using the programs. Okay, so solving linear algebraic equations, that's when we're going to use this left-hand division that we talked about before. So if we have this system here, we have 3 equations and we have 3 unknowns. So basically we would be solving for x, y, and z. So you could solve this by hand, but that would be kind of annoying. You're going to have to do that, of course, in some of your classes, but we can also solve this inside of MATLAB using left-hand division. Okay, so again, we have this system of equations here, and we want to solve for x, y, and z. So let's first write all of this out. So I'm going to define a matrix called A, and we're going to fill in everything here that's on the left-hand side of the equal sign. Okay, so that'll be our matrix A. So 6, 12, 4, that's our first row. 7, -2, 3, that's our second row, and then 2, 8, -9, that's the third row. All right, there's our matrix. Now I'm going to define a column vector B. This column vector B, it's called our forcing vector, so that might be some terminology that you hear sometimes. So our column vector B is 70, semicolon 5, semicolon 64. And then, again, we want to solve for x, y, and z. So to do that, all we have to do, and you'll see I use this terminology x underscore sol, so just meaning x solution. So often we have, you'll see an equation that's x equals x times b. So you might see this sometimes in your classes. So we have a equals x times b, and we're solving for this vector x here. That's going to be our solution vector. Okay, so I can solve for x, y, and z by just doing whatever variable name that I want to have. It doesn't matter. I can make this you're not going to call it apple. It doesn't matter. We'll do A backslash B. That's our left-hand division. And then we see apple equals 3, 5, negative 2. So this means x equals 3, y equals 5, and z equals negative 2. Okay, any questions on that?
How do you switch to like the left-hand division on the keyboard?
It's just above your enter sign. Well, enter.
Oh yeah, I see it. I see it. Yeah.
Okay. So again, this maybe isn't like a huge part of this class, but solving these linear systems of equations is going to be something that you do quite often in a lot of your classes. So, if you have to solve it by hand and you want to check your work, you can just go into MATLAB, define that system of equations in MATLAB, and then solve it, and you can make sure that your answer is correct. Okay, so we're just about out of time, so I think I'm going to stop right here, but I want to talk about the homework and the quiz. Okay, so we have a question to explain in more detail A divided by B. So we'll go over that really quick again. So that's basically our syntax that we have to use to solve this system of equations. So I'm not going to go into, as much why it's A divided by B. That's more for like a math class, but in this case, we have a matrix A here on the left-hand side, and then we have our matrix B on the right-hand side. And we want to solve this system of equations for all of our variables x, y, and z. So we know our matrix A, and we know our matrix B. So to solve for all those variables, we have to do A divided by B, where we're using that left-hand division. So the theory behind it is more for what you'd find in your math class. I'm just showing you how to solve this inside of MATLAB. Okay, so so the homework that's due tonight. So don't forget that it's due by 11:59 p.m. Remember that this is completion based, but I want to see that you actually make an effort to solve the homework and that you solve each problem in the homework. I'll upload the solutions either late tonight, so like after 12, or I'll upload it early tomorrow morning. And then our quiz, that's on Wednesday. That'll be at the end of class again. And if I have the same amount of work as the first quiz, then I'll give you 20 minutes. But I want to be around 15 to 20 minutes for the quiz. But seems like we should add a little more time, if we have the same amount of work as last time. So I want to make sure that everyone has time to actually complete the quiz. And this time I'm also going to make it worth more points. Maybe I shouldn't say that. I'm going to have the quiz will have more points in the quiz, but each quiz is going to be weighted the same. But this way, if you get part of the question wrong, I'm going to be able to give you more points for that question. So basically, I want to maximize the amount of points you guys get on the quiz. That's really it. All right, any questions on the homework or the quiz?
Professor, when is this video going to be uploaded, and when are the slides going to be updated as well?
So the slides are up now. I did have just that one slide I need to update, so I'll do that right after class. And the video is going to be as soon as I can get it up, which is, I start uploading right away, then it takes a while to process. So maybe in like 3 to 4 hours. YouTube takes a really long time to process it.
Okay. All right, thank you so much.
All right, so any other questions? All right, if that's it, then I'll see you guys on Wednesday for quiz 2.